First of all, let me thank Rose Hill Operating, that used to be TEMA Oil and Gas, and Brian Ayers, the Vice President of Exploration and Vice President of Geology and Acquisitions at Rose Hill, for the permission to publish this paper. I had worked the Delaware Basin for TEMA and Rose Hill, their subsequent after they went public, for about 6.5 years, so it was very nice. Okay, so just to read the outline slide to you, we're going to look at some methods that are used to define overpressure, and of those methods, what I have chosen is drill stem test, mud logs, and resistivity logs. And those, I believe, tell the bottom line of what I'm arriving at here as far as my conclusion. The Delaware Basin overpressure cell as currently defined is basically where did we have to mud up and in order to drill through overpressure. When you look in detail at the overpressure seen on the resistivity logs, and we'll get to how we see that later, it does not match that where we currently have to mud up. So when I compare drill stem test data to resistivity data to the mud weight data, and use derived pressure gradient and PSI per foot from drill stem tests, and mud weight derived pressure gradient, and then compare that to the resistivity derived pressure gradient, and compare a normal resistivity trend to an overpressured resistivity trend, you are able to see that the overpressure cell did exist throughout the entire Delaware Basin, but has been depleted in the western Delaware Basin due to laramide uplift and erosion. So let me just you can follow me through this work process and see if you agree with me or not. So let's just look at a standard pressure diagram. And of course, pressure or stress is increasing in this direction, depth increasing in this direction. This is overburden pressure, which would be about 1 psi per foot. This is the hydrostatic pressure or water gradient, and that's normally about a 0.45 psi per foot. And wherever we have the pore pressure increasing over a normal hydrostatic gradient, that's going to be the overpressured section. And of course, this is the point where if you overpressure it so much, you're going to have you're going to get that overpressure past your frac gradient. So this is just a standard diagram that y'all have all seen for a long time. So let's look at the methods to define overpressure. First of all, of course, there's seismic. I have these in the order that you would explore in a basin. So the first thing you do is you might shoot some seismic and you'd see a velocity increase in overpressure. Then you might drill a well or two, and you'd run a drill stem test, a repeat formation test, so forth, and you would find potentially some overpressure greater than a 0.45 psi per foot. Then if you did run a drill stem test or have a blowout or something like that, you would have to increase your mud weight in order to combat that overpressure. Then after you drill several wells, you're going to find a place to set a casing seat. So in previously drilled areas, generally where folks have to set that casing seat, that's pick the top of the overpressure. Then when you log your wells, you'll find a drop in resistivity or increase in conductivity on the resistivity logs. And of course on the sonic logs, you're also going to find an increase in sonic velocity. You're going to have an initial shut-in pressure from these drill stem tests or some other pressure test that you might have, and that's going to tell you an overpressure. That's going to give you an overpressure reading. Then, of course, a DFIT test, a diagnostic fracture injection test, that's going to tell you an overpressure reading. And then, of course, when you're finally producing the wells, you're going to have bottom hole pressure tests that are going to tell you whether or not you're in an overpressured environment. So the methods that we're going to use in this study are just drill stem tests, mud weights, and resistivity logs. Of course, somebody can go back and repeat this test with some of these repeat this work with some of these other methods and see whether or not they agree with me. Okay, so what is a normal pressure gradient in the Permian Basin? If you just had a normal brine, it would be about a 0.45 psi per foot, but the water salinities in the Permian Basin are 150,000 parts per million. So this gives us actually a higher natural pressure gradient. It's about a 0.48 to 0.49. This diagram is from Engel that basically looks at all the salinities of formation waters at different depths, the 150,000 parts per million, and that translates to 0.48 or 0.49 is a normal pressure gradient, hydrostatic gradient in the Permian Basin. So when I look at overpressure, I'm going to say that anything over 0.5 psi per foot is overpressure in the Delaware Basin. Okay, so the first thing I did was I looked at the mud logs. And there are about 1,000 mud logs that are available in the Delaware Basin. And the ones that I wanted to look at were the ones that, of course, went all the way through the Wolfcamp section, which is the deep gas wells. The deep gas wells that were drilled in the 60s and the 70s. So you got about 1,000 mud logs that are available, and I graphed 356 of the mud logs. Wells were initially drilled underbalanced when they initially started drilling the deep gas exploration. And then they found out they were blowing out, had all kind of problems. They started to drill overbalanced. So another thing that I'm looking for in this mud log is, does that well, are they walking the line? You know, of as they're drilling, you know, am I getting a gas kick, then I mud up 1/10 of a pound and I suppress that gas. I drill a little bit deeper and I have to mud up, you know, quite a bit in order to suppress the gas. Or am I just drilling underbalanced and flaring the entire time? So of the 356 mud logs that I looked at and graphed, essentially did a, you know, depth versus mud weight for each one. And so I'm able to essentially draw the overpressure from that mud weight. 113 of those wells had mud logs that were balanced. And then the other thing that I'm looking for is wells that also have a resistivity log in the same well, so only 39. So I'm starting out with 1,000 mud logs, and 39 of them have the database that I'm looking for. So what I'm able to do after I go through, and these are all the wells that had those mud logs, and this particular example is the Gulf Hayman well, which is right down here, right in Reeves County in the Tex Hayman field. And here's a perfect example right here. They're at 11.6, they get a little gas kick, they mud up, and they went mud up to 12-pound mud and stop that. So this is a balanced well. So what I then do is convert that mud weight to a pressure gradient using this equation. Depth times mud weight times 0.052 over the depth is going to give me a pressure gradient. And I do that 356 times. And here are those 356 wells. So this is a sum of the 356 wells. These wells in green here are those wells which did have to mud up, so they define the pressure cell based on mud weights. So when I look at, this is my Gulf Hayman well again, this is the gamma ray, this is the resistivity, this is the sonic log, this is the density log, and this is that pressure gradient as calculated from mud weight. And if you get a little closer, you can see some of these wells, and where I start to really go over above 0.5 is right about here. And at this point right here in this well, they got down to a 0.47, but it's below, here they're up at a 0.536. And so at this point, this Gulf Hayman well was drilling underbalanced, and then they went up to their pressure gradient down here is about a 0.65. So the top of the overpressure cell is right about here. The base of the overpressure cell is at the top of the Mississippian line. And this map is not a surprise. Anybody that's looked at the mud weights out in the Delaware Basin, this is virtually identical to a map that was published in 2017 by Shell. Rittenhouse wrote this paper here. So that's a very useful database that we have. Now that we've got 356 data points and a bunch of, we can define where the overpressure cell is, and we can do a lot of different things with that. We can isopack the overpressure cell. We can isopack the overpressure cell for different horizons. When you separate out the different stratigraphy of Wolfcamp A, Wolfcamp B, so forth, you can look at the average overpressure in a particular horizon. So it's a very useful database. So then you start to look at it a little bit closer though, and you find that the top of the overpressure from the mud weight, defined as when the pressure gradient goes above 0.0 psi per foot, occurs at variable depths in closely spaced wells. So right here, these two wells are, this is this line of cross section right here. And these two wells are pretty close in Loving County, gamma ray, resistivity. And this black line is that pressure gradient defined from mud weight. And as you can see, I'm defining very different pressure gradients very close to each other, and the top of overpressure is pretty significantly different for these closely spaced wells. And then, for example, right over here, here's a well that was drilled later, and they immediately mudded up. Yes?
We can't detect what you're pointing at. The cursor's not really very strong.
Oh, you can't see the cursor.
Yeah.
Okay.
Could you use a laser pointer?
And I don't have a laser pointer.
Oh, I
Shoot. I wonder if there's a way to, anybody got a laser pointer?
Nope.
I can just wander over there and, can you see the line, the black line?
Yeah.
Okay, so that's pressure gradient defined by mud weight. In this well right here, they went from about a 9-pound mud up to, I don't know what pound of mud that is, but this is a 0.9 over here, so that's about a 0.6.
Okay.
So in this particular well, and this is the top of overpressure right here, that'd be about a 0.6 psi per foot. In this well, and my point was that these two wells were very close, and I'm immediately going up to about a 0.6 psi per foot pressure gradient, and over here, I'm just barely getting above 5 right at this point, and then leaping up to 0.6 psi per foot. So it's an erratic. If I'm just looking at, is that a?
I've got a pointer.
Oh, okay. Let's see if I can use that.
Yeah, it's this red part.
Okay. Okay. Thanks.
Oh,
Okay, there we go.
okay.
Okay. So while I'm standing here making these comments about how mediocre the mud log pressure gradient per foot is, what I notice is that the resistivity drops pretty significantly at the top of the Wolfcamp in each one of these wells. So what I'd like to know is, can I use this resistivity, this drop in resistivity, and calculate a pressure gradient from that? And lo and behold, lots of other folks have done a bunch of work on this. And first of all, this graph is from paper by Bowers and Katsube, Roll of Shale Pore Structure and Sensitivity of Wireline Logs to Overpressure. So when we look at this in the resistivity log, here's a gradual increase of resistivity with depth in a normally pressured section. When I hit the overpressured section, that resistivity drops. A gradual increase of sonic, or a gradual decrease of sonic velocity with depth, and then a rapid increase of sonic velocity when I hit the overpressured section. The density just increases with depth. And here's this mud weight showing me where the top of the overpressured section was. So resistivity and sonic logs both have a distinct response to overpressure, and they are responding to changes in the fluid transport properties of the rock as altered by overpressure. Overpressured rocks are more conductive due to that increase in pressure has introduced a microfracture network. It has opened up the pore throats. So I've gotten more conductive and less resistive. So that's actually a pretty key slide right there. So let's look at a couple of real life examples from basins that we know something about, which are, or that I know something about, which are Delaware Basin and the Anadarko Basin. So first of all, this is an example from the Anadarko Basin. So in a normally pressured area in the Anadarko Basin on the northwest shelf, this is gamma ray, this is resistivity, and that resistivity is just gradually increasing with depth. This is about 33,000 to about 8,000 feet right here. The bulk density is gradually increasing with depth. In an overpressured area, however, in the Anadarko Basin, if it's overpressured, that resistivity decreases once you hit the overpressure. So let's look at a Delaware Basin example of a normal pressure gradient. And the other thing, let me emphasize, we want to only look at the shales. We're not going to look, you're going to have a resistivity change if you hit a sand, a resistivity change if you hit a carbonate, so we're only going to look at the shales. So this is a Delaware Basin log from the northwest shelf of the Delaware Basin, and I've highlighted arbitrarily where the shales. And that was an arbitrary decision. Where am I going to pick up enough shale so that I can look at the resistivity? And the trend of resistivity in this well is just gradually increasing with depth. This well is not in the overpressured section. The bulk density is behaving like it should and gradually increasing with depth. Yeah, and the reason we know this is because all nearby wells were drilled with 9 to 9.5 pound mud, and it was not an overpressure. So then let's go back and look at the Gulf Hayman well, which we know from its mud log was drilled in overpressure. And we have, okay, first of all, this is the gamma ray, and this is 21,000 feet, by the way, here, almost 22,000 feet. Top of the Delaware Mountain Group is right up here. Top of the Mississippian Limestone is right here. Wait a minute, this is the top of the Miss, this is the top of the Devonian. This is the Woodford Shale right here. So I've got the shales highlighted in black, the sandstones and the carbonates down here are not highlighted in black, so I'm only going to look at the shales and the resistivity values in that shale section. And I see a trend of resistivity increasing gradually with depth. I see that same kind of trend increasing on the sonic log, but we're not going to use sonic logs in this venture. So when I look at this, I see the trend of shallow resistivity, and here it drops in the overpressured zone where the Gulf Hayman well had to mud up. Can I look at this shallow trend and be able to calculate what this pressure gradient is here? Is there some relationship that I can draw between what that resistivity should have been if there was not an overpressured zone and compared to what that resistivity actually is in an overpressured zone?
Can you repeat that again? Sorry.
No, that's fine. I know that this area in here is overpressured, and I know that had it not been overpressured, that shallow resistivity trend would have just continued down like this. But it's dropped. Is there a mathematical relationship between what this trend should have been over here and what it actually is? And how would I define that? For example, if I had, a drill stem test right in here, or a production test right in here that showed me that, yeah, this is, 0.8 psi per foot, then I should be able to establish a mathematical relationship between the two of them.
Thank you.
Yeah. And has this been done before? And lo and behold, it has. It has been done in the Gulf Coast. So this is a well from West Cameron. And sure enough, this is a resistivity log, and there is a shallow resistivity trend. The well had to mud up here, and this is the decrease in resistivity in the overpressure. So this is the shallow resistivity trend, and we could, they could make an XY line along that. That's a shallow trend. But this is exactly what the resistivity is in the overpressure. So if I looked at a pore pressure gradient, so I've presumably have a bottom hole pressure test right here, and I can plot that right here, pore pressure gradient, PSI per foot, 0.85 in this example right here. And I look at the ratio between what this resistivity ought to have been and what it actually is. So that's the ratio of the normal trend versus the observed trend. So I'm looking at the shale resistivity ratio, what the normal trend should have been, but what it actually is. And so that ratio right in here, it's 2.8, and I enter this graph, go up, and sure enough, that's a 0.85 PSI per foot. So this is the relationship that has been established in the Gulf Coast. You just look at the shallow resistivity trend compared to what the observed resistivity trend. So what I want to do is I want to take this relationship right here and go into and create this chart, but make it specific to the Delaware Basin. So what I need is I need a bunch of pore pressure readings in this zone. I've got 39 or 55 resistivity logs. I need a bunch of pore pressure readings right in here. Where can I get those? I can get them from drill stem test data. Okay, in the Delaware Basin, there's the American Institute of Formation Evaluation database of drill stem test evaluation, where they have extrapolated what the pressure gradient is from drill stem test data. And that's the distribution of these wells that we purchased, that Rose Hill purchased from the AIFE database. So, AIFE database wells with calculated pressure gradient from an extrapolated drill stem test bottom hole pressure. 48 wells contain Wolfcamp or Bone Spring drill stem test data and have a calculated bottom hole pressure projection. And guess what? It's on low quality drill stem test due to low permeability rocks. If you're in the Gulf Coast, you got all kinds of beautiful pressure tests and beautiful permeable porous sands. What do you have in the Delaware Basin? You've got miles and miles of railroad track shale, and it's tight. Low permeability formations in the first, second, and third Bone Spring sands and the Wolfcamp. The first, second, and third Bone Spring carbonates, they're all tight. The shales are all tight. So what's the quality of those bottom hole pressure measurements in the Wolfcamp? Only 18 wells are located in the overpressured area of highest interest in the Delaware Basin. But these pressure gradients can be compared to Permian Basin log resistivity data. So y'all see what I'm trying to do here. I'm trying to create that Gulf Coast chart, and I'm trying to do it in the Delaware Basin. Okay, the red dots are all of those wells that I had a resistivity log on. The green circles are those wells that I had an AIFE drill stem test with a calculated bottom hole pressure. And I paired that with a real close resistivity log. I think only 2 of them had a decent resistivity log. So I've paired them with a very nearby well. These are those well pairs. There's 18 of them. This is the pressure gradient from the AIFE drill stem test data, 0.44, 0.58, 0.65, 0.79, etc. This is the observed resistivity in that section where the drill stem test was taken. And this is what that resistivity should have been if I look at that shallow resistivity trend. So then I'm able to take let's go back to, what I'm looking for is this shallow resistivity trend. What's this value? And compare it to this one here. And I'm doing that for these data points. This is the observed resistivity. This is what it ought to have been. What's that ratio? So then let's plot this pressure gradient against that ratio. And that's how we create that same chart. Pressure gradient measured from drill stem tests, and then the ratio of the normal trend, what it ought to have been, versus the observed, what it actually is. And sure enough, it's a trend. It's not that great, it's only a R squared of 0.45, but it's a trend. Now, when I place the Gulf Coast, here's the Gulf Coast field of data is right in here. But in the Delaware Basin, it's spread out all over the map here. Now, so then I'm able to have a mathematical relationship between normal and observed resistivity and pressure gradient. Why is this so scattered out? I had crappy data to start with. I only had 18 points to start with. Delaware Basin rocks have higher resistivities and a greater resistivity contrast in overpressure. And then why are there, in the Gulf Coast, there's tons and tons of data points. Why are there so few data points, so few drill stem tests? This is just a little aside here. Delaware Basin's overpressure, difficult to test with the high likelihood of blowout. The first well that I went out on in 1975 was the Texaco Dam Site unit. And I believe that there was a drill stem test in the neighboring well in the Wolfcamp. They had so much gas, they had to stop and test it. The valve assembly at the surface of the well froze because so much gas was flowing out of there. But there's gas for sure, but there's nothing in the Wolfcamp. The reservoirs are only as big as this room. It is so impermeable, there is no point in running a drill stem test. And as you all know, the biggest reserve addition in the United States, maybe in the world, is the Wolfcamp. Okay, so what we want to do is we want to go and take that calculation, take those two equations, put them together, and calculate a bottom hole pressure for each one of those resistivity logs. And this is you can come up and do this procedure and do it 55 times for each one of the wells, and you'll come up with a pressure gradient curve derived from the resistivity log. And here it is. Here's our Gulf Hayman well, and here's the Oxy Guthrie, which is a well that's pretty close to there. Once again, gamma ray, and I did only use the shale values. This is the resistivity curve. You can see top of overpressure starts right there, and all of this reduced resistivity log is in the overpressure. This black line is the mud weight calculated pressure gradient. And here, when we look at the Oxy Guthrie, here's the mud weight calculated pressure gradient, and that's a really close match to the red line, which is the resistivity calculated pressure gradient. So that's a pretty good match. In the Gulf Hayman well, it doesn't match so well. Now, why not? I'm not sure. One of the weaknesses in here, when you're picking a shallow trend, that shallow trend, the slope of that line is very important. I went back several times and re-picked that slope so that I could try and get this mud weight resistivity pressure gradient calculation close to the resistivity. And sometimes I've had a really good match and sometimes I did not. So, but what that gives us is, here's the top of overpressure from mud weight, and here's the top of overpressure from the resistivity. Now, there is a lithology correction. A fellow in 2018 had presented a paper up at ERTEC that when you are in a sandstone, there is a lithology correction that can be made. And right here, this is about the top of the third Bone Spring sand is right in there. But when I actually looked at all the data, the only place that I would move this to is I would put the top of overpressure from resistivity below that bubble that I see on the resistivity log that is because of that sandstone lithology in the third Bone Spring sand. I wouldn't really move it very much, so that's something that someone could do at a different time, is to make that lithology correction for the third Bone Spring sand. But I tried to be consistent. Where did my mud weight get above 0.5 psi per foot, and where did my resistivity log get above 0.5 psi per foot. Okay, this is actually the line of cross-section that was on a previous slide, but let's look at a couple of these cross-sections across the Delaware Basin, and I think, let's look at this goes across the southern Delaware Basin from kind of the Alpine High area down into the overpressured. So I have top of overpressure defined here. Once again, this is gamma ray resistivity. You can see the sag and resistivity here, and the corresponding pressure gradient calculated from the resistivity curve. This is a mud weight. As you can see in this well, that mud, they never had to mud up above 9.5 pounds, but the resistivity is telling me that this is overpressured. So how can I just explain that discrepancy? Here's another one with overpressure. Here's another one that, oh yeah, that's our Gulf Hayman well again. Top of overpressure based on the resistivity log, top of overpressure based on the mud weight. This is the overpressure cell as we currently know it. But when I'm looking at all of these resistivity logs here, here's another one. Here's the mud weight defined pressure gradient, says no overpressure. The resistivity says yes, I'm in overpressure. So how do I explain that? And what I'm going to show you is several isopachs of the gross interval top of overpressure to base of overpressure, and then only the overpressured section as we currently know it. Oh, and this is cross section 2, and essentially we're seeing the same thing. Here's this black line is the mud log pressure gradient, and this increase in resistivity, the decrease in resistivity and the corresponding calculated increased pressure gradient you can see right there. Here's another one, 9.5 pound mud, never increases, but the resistivity shows me that I have been in overpressure. And here when we get down to the actual overpressured cell, sure enough, I've got the mud weights are responding to the overpressure and the resistivity logs are responding to the overpressure. And some of those calculations are matching really close. So let's look at that gross isopac of the entire overpressured section, line log cross section 1 and line cross section 2. This is 1, this is 2. Everything in pink is currently overpressured. Everything in yellow and pink is telling me what was overpressured. So when I make that isopac of the gross overpressured area, it matches the isopac of all of the Permian units in the Delaware Basin. Right up here you can see this is the top of the Delaware Mountain Group, and this is the base of the overpressure. So you have to remember, from 250 million years ago into the Permian to Laramide time, this was the structural attitude of the whole Permian Basin. It was pretty much flat. The whole thing was overpressured, and it sat there overpressured for a couple 100 million years. So there's a couple of inferences that you could make about that as far as the porosity, the permeability, thermal maturity, a number of inferences that you can make. So this was the overpressured cell before Laramide, before about 50, 60 million years ago. And then, what's the current overpressure cell? This is just the isopac of the pink. Here's the current overpressure cell. So what happened here? And this is only the isopac of the yellow. All of this area was overpressured, and it has since leaked off due to the uplift of the western side of the Delaware Basin, starting in Laramide. Starting at Laramide times, this has been at least 3,000 feet of uplift and erosion on the west side of the Delaware Basin. And where else in the world can we find this? Well, actually you can find the same thing up in the Anadarko Basin. And this study was done with a lot more drill stem tests on permeable marl sands. This was the outline of the overpressured area in the Anadarko Basin, and here's the current outline of the overpressured cell in the Anadarko Basin. This is the data spread of data that they used to calculate that. And essentially, when you look at both of those basins, they really have had a similar history. The western side of the Anadarko Basin was uplifted, in Laramide time. The western side of the Delaware Basin was uplifted in Laramide time. Pressure leak off, pressure leak off. This is what that original overpressure cell looked like in the Delaware Basin, and this is what the current pressure cell looks like. That's it, simple. Okay, so what have we done? We have compared drill stem test pressure data to resistivity data to mud weight data, derived a pressure gradient and PSI per foot from all of these, and come to the conclusion that overpressure has been depleted in the western Delaware Basin due to laramide uplift and erosion, very similar to the Anadarko Basin. End of story. Thank y'all for listening. Are there any questions? There are a lot of implications to this study. Does the how does the overpressure cell affect your production, and what increase in production can you expect? And of course, that's how come I started doing this study. And no, the only key thing that I really am going to say about it is, yep, pressure leaked off to the west. When you look at thermal maturity in the Delaware Basin is related to both the original 200 million years that it sat, points, what is it, statistically significant has to be 21 data points. Well, here I'm trying to make that, that relationship here with, yeah, okay. Now, when you look at this, I mean, the R squared of 0.45, that's not very good. And say this point down here and this point up here.
Maybe that's one of the points you should have thrown out, is where I'm getting at. It's like if you had if you culled it out and said,
yes,
okay, I don't have 21,
mm-hmm,
but I have a better correlation with the wells that I was able, looking at the actual curve of that
mm-hmm,
star reading,
mm-hmm,
and say, hey, I turn a corner and I can project a pressure number that I like.
Right. Yeah. It is entirely possible that I could have gotten a better R squared if I had thrown some of these data points out. But then as I progressed all the way through the study and had, let's see. Oh, I'm going the wrong way. And had right here a pretty close match, with from my pore pressure gradient for a balanced mud weight well, for a pore pressure gradient derived from the mud weight and that derived from the resistivity, and I'm still using that R squared of 0.45, I went with it and said, oh, okay, that's probably pretty good. The sources of error in this calculation are exactly what you just said. Is that a crappy drill stem test? Should I have thrown that out? And then how did I pick this shallow resistivity trend? So I went back and picked those several times and came up with the best fit that I could and came to this point. Now, what other sources of pressure data would we have? There's a jillion DFIT tests that somebody must have in the Wolfcamp A and the Wolfcamp B. Let's see. So that I am assuming that there are lots of other pressure tests right now that would really, for the Wolfcamp A and Wolfcamp B, that would fill in this curve and maybe change that R squared a little bit better. Is that going to change the basic conclusion that I've come to here just for this? No, probably not, because basically I just said a basic thing, which kind of, when you think about it, of course, Of course, all that pressure, you know, depleted to the west, and the resistivity logs show it. So, but what you said, yeah, that is the weakness, then that slope of that line is a weakness, then another weakness, and I was telling you about that there are, you know, issues with this, a lithology correction. In order to make that lithology correction, you're gonna have to go to sonic logs and density logs. And that's a completely different, well, the trend of the shallow sonic log compared to what the sonic velocity is, that's going to be the same principle, but you're going to work with a different set of equations, and you have to have a density log all the way to the surface. It's real hard to find a damn density log all the way to the surface in the Delaware Basin. Yeah, so, yes, Marsha.
On that note, maybe you run a number of different sensitivities based on different criteria, and then maybe you just use Olympic scoring to toss out the highest and the lowest, and then concentrate on the 16.
Sure, yeah. And so if a person wanted to tighten this study up to actually make a better comparison to what the ultimate question is, which is what you had, is, okay, how can I relate this back to production? Then you would bring in all of those Wolfcamp A and Wolfcamp B defit pressure test data and tighten this curve up quite a bit. So, yes.
Very impressive presentation. I'm
Thank you.
really impressed. This graph here, you're looking at it, this is logarithmic scale, right?
The relative scale?
Logarithmic scale, no.
Logarithmic.
Oh, yes, logarithmic scale, yes.
I would assume if you use normal scale and take the exponential trend, you might get better results. That's number one. Just a suggestion.
Okay, yeah.
Number two, when you do have a kick or coming from the RFTs or from the sand and take the DST or the RFT, this is, you measure the pore pressure in the sand, not in the shale.
Mhm.
Then when you take that value and you throw it in the shale, this is not right. It is 90% or 80% right, but you get 20% wiggle room.
Uh-huh.
You're gonna look at the mud log and you try to figure out the difference between the pressure of the sand and the shale. But you had a great presentation, and if you look at Bauer slide,
Mhm.
you see that the gradient slope is negative,
Mm-hmm.
because when you calculate the gradient from the Kelly bushing, it's not right. The gradient is two values divided by the difference in depth. That's
Uh-huh.
the gradient. But if you calculate it from the Kelly bushing, you're gonna see, okay, can you get the Bauer slide back there?
Are you looking at this one? No, wait a minute.
No, the
Go back the
Bauer's.
other way. Not
That's
this
it.
one.
Yeah, one more.
This one.
This one.
Mm-hmm.
You see the circles at the, okay, the right, the equivalent mud weight?
Uh-huh.
Okay, you see the circle down, keep down. See that negative slope?
Ah, okay.
Because this is what's calculated from the Kelly bushing.
Oh, okay. I didn't know that.
Yeah,
Uh-huh.
the gradient should be between two values divided by the difference in the depth.
Huh.
That's what the gradient is. But
Okay.
anyway, you have a great presentation. That's
Thank you very much.
Appreciate it. Thank you.
Got one more question,
Yes.
just because I don't work in Delaware, but, so they set two strings of pipe, one above the cell and one below it?
Where they usually set pipe is, well, let me go to longer cross sections.
The last cross section would be a good one. Yeah.
Yeah, they will set pipe above, like in the rustler way up here, then they'll drill through the salt section right here. They will set pipe right about here at the top of the Bone Springs, or in the top of the Wolfcamp. The deep gas wells would be setting pipe in Wolfcamp A most of the time. And some of them, what they would drill, they'd do that d-exponent calculation in order to pick where where they were going to set pipe on the early wells. By the time I got to the Delaware Basin, they pretty much already knew where to pick that, but they were still like walking that d-exponent down, doing that calculation like every day to try and decide how deep they could set pipe. But so there'd be a casing string set right here. I guess that'd be one of them right there. Let me find an irregular. Here's a casing. The casing string was set right there. So set casing right there, and then get down below into the top of the Mississippian line. Also a very difficult pick, where the areas where the Mississippian was very thin in the southern Delaware Basin, and they'd set another string of pipe here. The lower Paleozoic section in the Delaware Basin is normally pressured.
Lots of lost circulation, is that how they pick that point?
The Kelly starts to bounce right here. Well, this is a churty lime, and when you pick the top of the miss right there, you set that pipe in the top of the churty lime, and then you don't have to worry about overpressure from that point on. Yeah.
Same like the subsalt in the Gulf of Mexico. When you go under the salt, your pressure drops.
Ah. Okay.
Everyone, thank you very much. We were delighted to have